Hello and welcome. In this lecture we're going to continue talking about degrees of freedom and how what you specify to exhaust the degrees of freedom is equivalent to a control structure. In other words, degrees of freedom, specifications and control go together. That's what we're going to see in today's lecture. So let's look at this very simple A plus B goes to C process, which we have looked at before. So you got A and B mixed with recycle AB going into a CSTR, a reactor. A and B react exothermically to produce C. The reaction heat is removed by a coolant. Single pass conversion is, let's say, 30, 40, 50%. So the reactor effluent is a mixture of A, B and C. C being heavy is separated in a distillation column and leaves down the bottoms. Unreacted A and B leave up the top. That's your process. So now let's see, at the very basic level we have 9 control valves, 6 on the column and 1, 2, 3 and 6 on the column. So that's 9 control valves. So the control degrees of freedom is 9, and let's say the operator specifies the position of all these 9 valves. That's the way we are running the process. Well, that's not a great way of running the process. All of us would agree with that, and that's because you have no control on the product purity. C, of course, being heavy will drop down, but you'll also get A and B, and the product is not pure. How much A and how much B you're putting in, there's no relationship, whereas in a process you want 1 mole of A to react with 1 mole of B, you see. So you may be putting in 95 moles of A and 105 moles of B, for example. Yeah, and so on and so forth. Let's say the more reaction heat is being removed, more reaction heat is being generated than is being removed by the coolant. In that case, the reactor temperature will increase, and if it's a highly exothermic system, you may get unstable reactor runaway and an explosion. That can also happen because the energy balance is not closed on the reactor, and so on and so forth. So because of all these issues, running the plant, what are the specifications corresponding to this control structure? It is the 9 valve positions. Running the process this way is not a great idea because you get drifting material and energy inventories. The process is never steady, and there's guaranteed breaching of safety limits. I just talked about temperature runaway in the reactor. No product quality control. Yeah, the product is whatever it is. You can't guarantee quality to the customer. So this is not the best way of running it. So you say, okay, let's put in a control system on it. So here's a control system that has been put in. So you have flow control for B, flow control for A. Reactor cooling duty is manipulated to hold the reactor temperature. Reactor level is controlled by manipulating the reactor effluent. On the column, level control at the bottom by adjusting the bottoms rate, level control in the reflux drum by adjusting the distillate rate, pressure control by adjusting the column duty, reflux under flow control, reboiler duty is specified. That's the control structure that we have. So in this case, what are my specifications? I am specifying FA, FB, T reactor, level reactor, L, which is reflux rate, column pressure, reflux drum level, sump level, and reboiler duty. So the specifications are FA, FB, T reactor, V reactor, L, Q, P col, V reflux drum, and hold up in a level in the sump. Hold up in the sump. These are the other specifications. Here again, the problem is if more A or B starts dropping down the bottoms, reboiler duty is what it is, then the product is not guaranteed to be pure again, or you don't have any quality control on the product. That's the problem. Also, if A isn't being put in excess than B, then the excess A, or whichever is the excess reactant, whether it is A or B, has to have a way out of the process. So that excess A or B will have to be coming out here. Again, because of that reason, you don't have quality control. So you say, well, process will settle at a steady state, but high product purity is not possible because any excess reactant must exit here. And we are not ensuring A and B are in stoichiometric ratio. So that's the problem with this control structure. So you say, okay, if you want product quality control, what we will do is we'll put in a temperature controller here. And so what we have done is we've put in a temperature controller here, and A is independently specified by the operator and B is maintained in ratio with the A flow rate. So there must be a line going, there must be a line going from here to here. So if A flow increases, B flow is increased by the ratio controller. So in this case, specifications are FA, the ratio of B to A, reactor temperature, reactor volume, reflux to feed ratio. That's here, reflux to feed ratio, column temperature, column tray temperature, column pressure, hold up in the reflux drum and hold up in the sump. We may think that because there is a temperature controller, this will give us good product quality control, but yes, it will give us quality control in the sense that if the temperature is maintained, then the quality of C is maintained. Quality control is there, but the process is not stable because if either A or B is in excess, the temperature controller does not allow that excess A or B to drop down the bottoms. So whichever fresh feed is in excess, that will accumulate in the recycle loop. And this is like if you have a tank and if you're specifying fresh A and fresh B, you're specifying flow in and flow out, and if these two flows are not equal, then the level is either building up if inflow is more than outflow, or it is depleting if outflow is more than inflow. In other words, the tank level is not steady. It's either depleting or building up. And if that is the case, eventually the tank level will reach a alarm limit, either high level alarm will go off or the low level alarm will go off, and you will require operator intervention. Similarly, in this process, if you treat this process as a tank, you're putting in fresh A, you're putting in fresh B, and you're taking out C. You specify fresh A, you keep B in ratio with A, but nevertheless the amount of A that's going in and the amount of B that's going in can be slightly off because of flow errors, and therefore because the temperature controller on the column does not allow any A or B to leave down the bottoms in the product stream, any excess A or B, whichever is in excess, that will build up in the recycle loop until some constraint gets hit, some process constraint goes off. So the specification set is this. However, this is not consistent. It is inconsistent. Inconsistent in the sense that the process does not settle at steady state. So this is inconsistent. And so the problem is there is the possibility of a stoichiometric imbalance. Excess reactant accumulates in the recycle loop. The process therefore is never steady. It is guaranteed to fail. The process will fill up. The recycle loop will fill up with the excess reactant. And most likely what will happen is the column will flood, because in order to keep the excess reactant from dropping down, the temperature controller will keep cranking up the boil up, and the extra boil up will eventually flood the column, not allow the liquid to drop down the column, and so the column will get flooded. So you will most likely hit a flooding constraint on the column. Okay, so that's the problem with this control structure. How do we take care of this? Well, one way of taking care of this is hold the composition here and adjust the ratio. This is what I had shown in the previous lecture, and that's what we show here. That's exactly what we are doing. Yeah, and in this case, instead of FB by FA, composition of B in the reactor is being specified. That's this guy. Now this guy does not allow excess A or excess B to build up in the loop. So let us say A is excess, then the A composition will start going up, B composition will start going down in the recycle loop. So if the B composition starts going down, what the composition controller will do is increase this ratio, and therefore more B will be brought in and the B composition will get back, and A to B ratio will then be brought back to stoichiometric, to exactly stoichiometric. Alright, so there is no drifting mode in this. It closes all material and energy balances, including the stoichiometric feed balance. And so here all balances are closed. It will drive the process to steady state. This is a good specification set. Good specs. Previous examples were bad specs. You could also have, for example, you could measure both A and B composition in the reactor and maintain A to B or B to A ratio in the reactor by adjusting the B composition set point. That's what is happening here. You're measuring A composition, and the B composition should be XB by XA times XA. That should be the B composition set point. So you maintain A and B in ratio. This is also another feasible, or shall we say reasonable, specification set that causes the process to operate at steady state while closing all material balances. And in this case, everything else is the same. This is the specification. Instead of XB reactor, it is XB by XA reactor. And in this case also all balances are closed, and this specification set is consistent and will drive, consistent or good, and will drive the process operation to steady state. There is no drifting mode here. So as you can see, what you specify is in your hands. So tremendous flexibility exists in what is specified corresponding to the available degrees of freedom. So here, this is that splitter example with 3 splits. For the control system shown, the specifications are flow through the first branch, flow through the second branch, and flow through the third branch. These are the specifications. Flow through the first branch, second branch, third branch, F1, F2, F3. But you could have, F1 specified, and then you are maintaining F2 in ratio with F1. So what you're specifying here is the ratio F2 by F1, and you also have F3 in ratio with F2. So what you're specifying here is F3 by F1 ratio set point. So in this case, what you have as your specifications are F1 and the two ratios F2 by F1 and F3 by F2, sorry, because the ratio is with respect to 2. Yeah. Is this the, there are other possibilities, and I'll just show another one. So you got the flow controllers. So F1 and F2 are independently specified. You add these two signals up, that's the summing block, and subtract it from the total flow. This is the total flow. Subtract it from the total flow that you want, the desired total flow, and the third flow set point, F3 set point, is then F3 set point is equal to F dot set point minus F1. We are taking the set point, so F1 set point minus F2 set point. Yeah, that's what we are doing here. So the specifications are F1, F2 and F dot. F1, F2 and F dot. There are other possibilities, infinite possibilities. I've just shown 3 of them. Let's look at a distillation column. In the distillation column, here what we have as the specifications are, see, the levels don't affect the steady state, and pressure you're not free to change, so we'll exclude the 2 level set points and the pressure set point as specifications, because these level set points don't affect the steady state, and pressure set point, you're supposed to operate the column at the design pressure. You're not free to change the pressure set point, because if you change the pressure set point, then temperature is not a direct measure of composition. So in this case, excluding the 2 levels and the pressure, what are the specs? Feed flow, reflux rate, reboiler duty. Here, same control structure, but now we start adding on top of it. So what I'm now doing is keeping the reflux in ratio with the feed. So I have L by F here, set point specified, and adjusting the reboiler duty to hold a tray temperature. So I have a temperature set point here. So the specs here are this guy, and this guy, and that's exactly. And this S here denotes a stripping tray. So for this control structure, the specification set is this. There's another possibility. Now what I do is I take the previous control structure and build on top of that. So what do? I hold the bottom composition by adjusting the temperature set point, and I hold the top composition by adjusting the reflux to feed ratio. Okay, so in this case, X distillate and what is this? X bottoms and feed. These are the specs. Okay, so X distillate and X pot. These are the specs. So as you can see, what you specify, implicit in what you specify, is a control system. Let's look at some other possibilities. Here's another one. So here what we are doing is, so here what we are doing is, the temperature on the column is controlled by adjusting the fresh feed flow. Reflux is maintained in ratio with the feed. Q is free. So here instead of specifying the fresh feed and setting the processing rate of the column, the processing rate of the column is being set by specifying the reboiler duty. How does this work? Well, if you increase the reboiler duty, you'll get more boil up here. If the boil up increases, the temperature will increase. If temperature increases, the temperature controller will bring in more cold feed to reduce the temperature. So this is how this works. Yeah. So if Q increases, temperature increases, and then the temperature controller causes the fresh feed to increase. So this is how the processing rate is changed. So the processing rate, the set point adjusted to bring about a change in the processing rate, is this guy. So Q is the manipulation handle used to bring about a change in the processing rate. In the previous control structures, it was the fresh feed to the column that was used as the processing rate manipulator. So this manipulation of processing rate, the set point used to manipulate the processing rate, is also referred to as the throughput manipulator. Throughput manipulator, TPM. And this control structure corresponds to these as the specs, where this is the TPM and these are the 2 specs corresponding to the steady state degrees of freedom of the column. You could have the TPM on the distillate And then to hold the reflux drum level, you could manipulate the steam to the reboiler or reboiler duty. And how this works is, well, if this level, let's say the level goes down, level of the reflux drum goes down, then this level controller causes Q to increase, and as Q is increased, you get more vapor going up, which pressurizes the column, and therefore this causes the pressure to increase. And because the pressure is increasing, the pressure controller says that, oh, you got to condense more to bring the pressure back to set point, and that causes QC to increase. And as Q condenser increases, the liquid going into the reflux drum increases, and therefore level gets back to set point, and this causes level to go back down, back up. So the decreasing level is compensated by the level going back up. Yeah, so this is the cause and effect, the way it works. If the pressure controller is not on, level control of the reflux drum will not get achieved in this control structure. But nevertheless, this control structure will work as long as the pressure controller is on. You will get level control of the reflux drum. What are the specs here? This guy, this is the throughput manipulator, this guy, and this guy. These are the specs. Here's another one. And in this case, what are we doing? We have the throughput manipulator again over here. Yeah, throughput manipulator is again over here, and you're maintaining the reflux in ratio with the distillate rate, and everything else is the same as before. So here the specs are: distillate rate is the throughput manipulator, L by D, and instead of L by F it is L by D, and temperature of the stripping tray, that is controlled. So again, the point is, what you specify implicit in that is a control structure. So in summary, let me go back in. Yeah, so in summary, I hope you are now convinced that just by applying common sense, what am I free to change? If it is applied correctly, you can very easily calculate the degrees of freedom of a process. Control degrees of freedom is the number of independent control valves. It's also equal to steady state degree of freedom and dynamic degree of freedom. There exists tremendous flexibility in what can be specified for the steady state degrees of freedom. A good chemical engineer zeroes in on these specifications for a given process. And I hope you saw that implicit in every specification corresponding to the steady state degrees of freedom are controlled variables, and these controlled variables are controlled using a control structure. I hope you also see that depending on the control, what is controlled, it determines whether the plant will reach steady state or not. In the A plus B goes to C process, we did see that if you have the stoichiometric imbalance prevents the plant from going to steady state unless you put in a composition controller on the reactor or a composition ratio controller in the reactor. And every specification set corresponding to the steady state degrees of freedom, to the degrees of freedom, implicitly assumes a control structure. And so degrees of freedom, specifications, and control structure synthesis go hand in hand. They're all linked, they go together. If you understand degrees of freedom, a true understanding of degrees of freedom implies a true understanding of specification, which in turn implies a true understanding of control system or control structure synthesis, which all, so it all goes together. So that is what I keep saying again and again and again. It all begins and ends with degrees of freedom. If you have a good handle on degrees of freedom, you will be a great chemical engineer. And if you don't have a good handle on degrees of freedom, that's it. Kuch na ho payega. So with that, I'll end this lecture. Thank you all for your attention. See you again for the next lecture. Thank you and goodbye.